Measures of association. Here we're going to examine some of the underlying mechanics of statistics as well as applications of statistics to some simpler problems and special nominal cases of statistics. Univariate analysis, looking at the single variable. There are different measures of central tendency for the single variable. You have mode, median, and the arithmetic mean, which is more conventionally known as the average. So the mode is the most frequently occurring value in a distribution of scores, typically the biggest single block. Mode is not very stable since it can change if just a few values change and is highly sensitive to how categories are constructed. It is the only measure of central tendency available for nominal data. So if we were to have three political parties, the Liberals, Conservatives, and the NDP, we would ask which is the mode. It would be the political party that has got the most members out of the sample. There are many types of modes, unimodal, bimodal, and polymodal types of distributions that can occur and be visible in a sample. So here we have a number of political science courses taken by graduating political science majors. We have the number of courses in a column on the extreme left. Then moving to the right, we've got the number of students in those classes. We've got then the percentage of students in a column, and finally the cumulative percentage, which is the last category. Here, we'd be looking at percentage of students, which is the third column from the left, second from the right, and we're interested in the largest single block, and that would be 13.9. 13.9 percentage of students take a number of courses 18 in which there are 16 students. The median. The median, which is typically used for ordinal and interval level data, where ordinal level is ranked, like bronze, silver, gold, and interval level is real numbers, like height, weight, and time, refers to the value above which and below which are 50% of the cases fall. It is the midpoint of the distribution of cases, but not the midpoint of the scale. To find it, we number the cases from high to low, and it is the middle one if there's not a number of cases, or the midpoint between two middle cases if it's even. Returning to our previous value, we're looking again at the fourth row. We've got 47.8 cumulative percentage on the column in the extreme right, and this is pretty approximation of where about 50% of the cases are going to fall. Remember, the scale is also at 50%, but we don't use the scale, we use the cumulative percentage of where the students are distributed. Now, the arithmetic mean is the total sum of scores divided by the number of cases. The mean is sensitive to extreme scores, and so is less useful than a median or a mode when the distributions are skewed or are disparate, such as, there's one large value and many smaller values. Now, the arithmetic mean here is not that clear. We would want to calculate the total number of students, the total number of courses taken, and then work out the number of average students per class. And it cannot be done with the data in this table, which has already been aggregated. Now, in a normal curve, the mode, the median, and the mean are the same. Now, the tails in a normal curve are asymptotic. They approach, but they never meet the horizontal axis as they stretch out to the extreme left and the extreme right. Now, the distribution of the population can be described using standard deviations that we looked at before. 68% of respondents will be within one standard deviation of the mean. 95% of respondents or cases will be within two standard deviations, above and below the mean. Here, 95% minus 68% divided by 2 leaves us the 13.59% on the left and right side between the first and the second standard deviations. 99% of cases lie within 3 standard deviations above and below the mean. So here, 99% minus 68% minus 2 times 13.59% leaves us 2.15%. Here you can see the normal distribution, the Z distribution, which is the standard normal distribution. This is the F-statistic distribution. Here, the mean, the mode, and the median are not the same because of the way the F-statistic is skewed. So how do we calculate the standard deviation? And it should be pointed out the standard deviation is not the same thing as the standard error. The standard deviation is the average distance that values are from the mean. So in a sense, it's an average. The basic formula is the square root of the sum of I, which is any individual case, and if you have a list of cases, it's each of them, minus the mean of those cases, squared, and then divided by the number of cases. Now, if we're looking at a sample standard deviation, it's going to be n minus 1. We divide by n only when we're doing the standard deviation for the population. So let's look at how we calculate the steps. All right, here we've got the steps. And let's apply it to a case. So here we have 6 defense budgets in US billions of dollars, 20, 25, 30, 60, 70, and 100. And these are 6 cases numbered 1 to 6. So the first step is to find the mean. And we do that by summing the total defense budgets, 20, 25, 30, 60, 70, and 100, and they total to 305. We divide by the 6 cases, and that leaves us a mean of 50.83. Now in the second step, we subtract from the mean, we subtract the mean from each of the cases. So we have case 1, we have a value of 20, we subtract from it the mean of minus 50.83, which leaves us minus 30.83. For case 2, we have 25, minus 50.83, and that leaves us minus 25.83. Case 3, we have 30, minus 50.83 is equal to minus 20.83. And then we have 60 minus 50.83, which leaves us 9.17. And then 70 minus 50.83, which leaves us 19.17. And then 100 minus 50.83, which leaves us 49.17. The third step is then to square these values we calculated in the second column. And that the squaring of minus 30.83 is equal to 950.49 in case 1. For case 2, the squaring of minus 25.83 is equal to 667.19, and so on. We then, in step 4, total this value. So these 6 cases squared, their values, is equal to 4,920. That's the sum of squares. In step 5, we divide the sum of squares by the number of cases. This is going to give us the variance. Now, it depends if we're using the variance for the population or the sample. If we're doing it by the sample, we would divide by n minus 1. We do this because we want to be more conservative. And so by dividing by minus 1, we reduce the bias in the estimate since the sample underestimates the standard deviations of the population, typically. So, that then gives us the value of 820.14. So 4,920 divided by 5 will give us that value. Well, we're going to divide by 6 because we're looking here at the population. In step 6, we want to calculate the standard deviation. And we simply take the square root of the variance. So the square root of 820.14 will give us a value of 28.64. That's the standard deviation. So then how do we calculate the standard error? The standard error is going to be the square root of the number of cases. So it's going to be 28.64 divided by the square root of 6, which is going to give us 11.69, which is the standard error. The standard deviation is sensitive to extreme scores. Normalized or standardized scores of z-scores are represented as standard deviations. Converting to standardized scores is very simple. It's going to be the z-score equal to the value that the particular student has on, say, a test, minus the mean divided by the standard deviation for that sample or for that population parameter. So here again, you can see standard deviations, and so numbers would be described, values would be described as standard deviations above or below the mean. Here's the calculation for the standard error. Confidence intervals. So in a recent countrywide poll of 6,324 card-carrying conservatives eligible to vote in the party leadership contest out of a population total of 125,000 in that party, Peter MacKay received 35% support with a standard error of plus or minus 1.9%, while Kevin O'Leary received 20% support with a standard error of plus or minus 3.6%. So there are three questions, and these are very similar to the questions you'll receive on the midterm. Number one, what are the 95 and 99% confidence intervals around each candidate's support? 2. Based on this result, which candidate is most likely to win the candidacy of the Conservative Party, and why? And number 3, what could you do to increase your certainty about your prediction for the Conservative Party nominee? So question 1. What are the 95% and the 99% confidence intervals around each candidate's support? So this is the solution procedure. Number 1, determine the mean for each candidate. Right, the mean in this instant is the proportion of the total independent variable, which is specifically the electoral support among those card-carrying conservatives. So for Peter MacKay, it's 35% of 6,324. And that equals 2,213. That's the average number of voters. For Kevin O'Leary, it's 20% times 6,324, which is 1,264. The second step is to determine the standard error. So for Peter MacKay, it's going to be 1.9% of 6,324. And this is going to equal 120.156. For Kevin O'Leary, it's 3.6% of 6,324, and that's going to equal 227.664. Now these are values that are going to be added and subtracted. In the third step, we determine the desired confidence level. Now in the social sciences, this is typically a 95% confidence level. More stringent confidence levels, typical of surveys, can be 99%. So we need to determine the z-value multiplier. Now the z-multiplier is actually the standard deviation of a normal curve whose total probability value is 1. In other words, p is equal to 1. When seeking the z-value for a 95% confidence interval, we're looking for dispersion from the mean. So here we're going to take a look at the table. Whereas the z-table is cumulatively valued from left. So here you can see the z-value table. For the 95% confidence interval, this implies that an area valued at 2.5% will be outside of the confidence interval on both the left and the right side of the distribution. So 5% divided into the left and right equals 2.5% for each side. That means we start on the left at 2.5%, add 95% to that value, which carries us to a sum on the right of 97.5%, which is 2.5 plus 95 is equal to 97.5%. So on the right side, we locate the 0.975 value. Okay, let's go do that. So 0.975 is here. We can see that value here. And we can see that it's composed of 0.06 here and 1.9 here. It's the intersection. Now, change the values for the pointer option. For the 99% confidence interval, 99% confidence interval implies that an area valued at 1% will be outside of the confidence interval on both the left and the right side of the distribution. So 1% divided into left and right is divided into 0.5%. That means we start on the left at 0.5%, add 99% to that value, which carries us to the sum on the right of 99.5%, which is 0.5 plus 99 is equal to 99.5%. So on the right side, we locate 0.9951. 0.9951, which is this value here. Now we're looking for 0.995. We cannot find it, and 0.9951. So these are the description I just gave for the 95% confidence interval. This is the description for the 99% confidence interval. So to calculate the confidence interval, we take the mean and add and subtract the standard error times the z multiplier to get the range at that confidence interval. So the range is equal to the mean minus 1.96 times the standard error, and the mean plus 1.96 times the standard error. That's for the 95% confidence interval. For the 99% confidence interval, it's going to be the mean minus 2.58 times the standard error, and the mean plus 2.58 times the standard error. So for Peter MacKay, we have a mean of 2213, which we calculated above. And in the standard error we got from step 2 above, which is 120.156. So for the 95% confidence interval for Peter MacKay, it's 120.156 times 1.96, which is the value we got from the z-score table, is equal to 235. Now 2,213 minus 235 to 2,213 plus 235 gives us our 95% confidence interval, with a net set of supporters of 1,977 to 2,448. Now calculating this to the 99% confidence interval is going to be 120 times 2.58, which is the z-value for the 99% confidence interval. And this is going to equal 310. So it's going to be 2,213, which is the mean number of voters, minus 310, ranging over to 2,213 plus 310. So the 99% confidence interval is going to be 1,902 supporters to 2,523 supporters. So the 99% is more likely to enclose the true value. It's got a better confidence interval. So let's apply this now to the next candidate. So Kevin O'Leary has a mean of 1,264 and a standard error of 227.664, which is what we calculated in step 2 above. The 95% confidence interval is 227 times 1.96, which is the 95% z-score we got from the table, and that gives us 446. So we take the mean supporters, 1,264 minus 446, and that ranges to 1,264, the average number of supporters, plus 446. And that gives us a 95% confidence interval of 817 to 1,710 supporters. For the 99% confidence interval, it's 227 times 2.58, which is the z-score that we got from the table, and that gives us 587. And so we have 1,264 supporters minus 587 to 1,264 plus 587. And that gives us, in the 99% confidence interval range, 676 to 1,851 supporters. Now notice we are more certain of outcomes as we broaden the confidence intervals, even though it becomes seemingly less accurate because it covers a greater range. So question 2. Based on these results, which candidate is most likely to win the candidacy for the Conservative Party, and why? Well, it would be Peter MacKay, because at either the 95% or the 99% confidence interval, his range of support is higher than Kevin O'Leary and does not overlap with the values that Kevin O'Leary has. So at the 95% range, we're looking at 817 to 1,710 supporters for Kevin O'Leary, and Peter MacKay's got 1,977 to 2,448. And that's a much stronger block, and the two ranges don't overlap. At the 99% range, Kevin O'Leary's got 676 to 1,851, and Peter MacKay's got 1902 to 2523. Now notice that at the 99% confidence interval range, the values of Kevin O'Leary and Peter MacKay approach each other closer and almost overlap, but they don't. So the 99% confidence interval has a higher level of confidence. So question 3. What could you do to increase your certainty about your prediction for the Conservative Party nominee? So either calculate an ever-increasing confidence interval, perhaps at the level of 99.9%, or increase the number of respondents, n, to reduce the standard error. Standardizing values, calculating z-scores. So we have a problem here. We want to find out who's smarter, a political science student or a psychology student. So the calculation we're going to make is going to be the individual value that they have minus the average value divided by the standard deviation. And this is going to make it possible to compare the values for these two cases. So the political science student has an individual GPA of 3.2, an average GPA of 2.4, with a standard deviation in the sample of 0.6. And the calculation there is 3.2, the student's GPA, minus 2.4, the sample GPA, divided by 0.6, the standard deviation, with a resulting value of 1.33. The psychology student has a GPA of 3.4, an average GPA of 2.8, with a standard deviation of 0.6. 3.4 minus 2.8 divided by 0.6 is equal to 1.0. So how do we evaluate this? Well, the political science student has the more exceptional GPA because their value, standardized value of 1.33, is greater than the standardized value of 1.0. Nominal level measures. So one of the measures is called a PRE, a proportional reduction in error. And it compares the difference in the amount of error before and after the inclusion of the independent variables. Now, the mode is the best way to predict an outcome for nominal level data when you're simply looking at the dependent variable. So here we've got Liberal, Reform, and NDP. These are 3 different political parties that can be joined, and our goal is to predict which party a single individual will join. And we would guess that there's a 60% chance that an individual will join the Liberal Party. The Liberal Party here is the mode. They're the largest single block category. So let us conduct a proportional reduction in error metaphorical calculation. There's different variations of these calculations, and we're going to explore some of them. So in step 1, we want to determine the mode. And the mode is going to be all of the values added up minus the largest category, and this is going to give us the error without the independent variables. So we saw earlier we've got all of the categories together is going to be 100, and we subtract from that the mode, which is the largest category. So 100 minus 60 is equal to 40. So we have 40 errors which remain. Now we can carry that calculation to the next step. We would also subtract from that 30. 30 is the marginals and the residuals. And let's see where we get those. So here we've expanded the proportional reduction error to a model which includes the independent variable of region. So we have an independent variable of 3 categories, West, Central, and Atlantic. And we hope by including these independent variables, we're going to improve our ability to predict the candidacy, or rather the membership an individual has in the political parties. So how do we calculate the marginals and the residuals? Well, we calculate that value of 30 by looking at each of the columns, West, Central, and Atlantic. And so in West, we take the marginal, which is a 30, we subtract from it the largest mode. Now, so for the West, the mode is Reform. So it's going to be 30 minus 20, and that's going to give us a remainder of 10. For the Central region, we have a marginal at the bottom, of which is, marginal is basically a value on the outside of the table, typically as a part of a total. We have 40 minus 25 because the Liberals are the largest block in the central geographic area. So it's going to be 40 minus 25 is equal to 15. And then in the Atlantic column on the right, we have a marginal at the bottom of 30, and we subtract from it the minus 25, which are the liberals that membership in the Atlantic, and that is 30 minus 25 is equal to 5. Now, those three values, 10, 15, and 5, we sum them up to equal 30. And that 30 then gives us the next step in our calculation. We then divide by 40, which is the original errors that remain. So we can see here that for each column we would total the value modes, and we've already calculated this. We sort of covered that earlier. So for each column we total the values of the modes, and for each column we total the inverse, which are the totals minus the modes. And so for the column modes, we have the highest single value per column. We have 20, 25, and 25. And we total these into a value of 70. We also calculate the inverse modes. These are the column totals minus the column mode. And so we have, for the West, 30 minus 20, which is the reform. For Central, we have 40 minus 25, which gives us 15. And for the Atlantic, we have 30 minus 25, which gives us 5. And that gives us a total value of 30. And so we have in the example here 20 plus 25 plus 25. This equals 70. And then we have subtracted from it the 10 plus 15 plus 5 that we calculated earlier, and that equals 30. And so we have 70 minus 30 is going to equal 40. So the fourth step is going to be the overall calculation. It's going to be the error without the independent variable minus the error with the independent variable divided by the error without the independent variable. So this total calculation is going to be 40 minus 30 divided by 40 is going to equal 0.25. So the interpretation here is that we have an improvement of 25% by including region as an independent variable. Now there are other measures for nominal and ordinal data. There's the lambda, the Kramer's V, gamma, Kendall's tau B. Gamma and Kendall's tau B you would see in SPSS if you were to run a contingency table. These are very often used as hypotheses tests to see whether the addition of the independent variables makes a difference in being able to predict the dependent variable. So the way to calculate lambda, it's going to be the total modes of the model with the independent variable minus the largest row marginal divided by the total marginals minus the largest row marginal. Right? So what are the total modes with the independent variable? Well, for West we have 20, for Central we have 25, and for Atlantic we have 25. Right? Those are the largest blocks in each of the regions in the independent variable. We subtract from that the largest row marginal. And the largest row marginal, these are the marginals that are on total column on the extreme right. The largest row marginal is 60, which is for the Liberal Party. And we divide that by the total marginals. And these, again, these marginals are the values on the extreme right column, total column. So it's going to be 60 plus 30 plus 10, minus the largest row marginal, which again is the Liberals at 60 in the rightmost column, titled total. So that's going to be 70 minus 60 divided by 100 minus 60 is going to equal 0.25. Right? So 70 is the biggest category per column. It's going to be 20 plus 25 plus 25 minus the largest row marginal minus 60. So again, we have a lambda of 0.25%. Now the problem with lambda is that it underestimates the strength of the relationship between two variables when there is an unequal distribution among categories of the dependent variable. Now measures for ordinal level data also include gamma and tau B. These assume there's a linear relationship, and the computer can often be assigned to obtain these scores for us when we're using a contingency table. Now, the chi-square distribution. A chi-square is a very commonly used method of testing the independence of two nominal or ordinal level variables. This is something you need to know because it occurs so often. Formally, the chi-square test assesses the likelihood that the relationship observed in the sample is due to chance. Quote, how likely is it that we would find a relationship of the strength observed in a sample of this size if there was no relationship between the variables in the population? Note that chi-square is an inferential statistic and is not a correlational statistic. It does not show how much of an independent variable affects the dependent variable or how strong that relationship is. So here you can see a chi-square with different degrees of freedom. It actually has a different shape or a different bell curve distribution. So the skewness and the kurtosis of the chi-square is reduced as the number of cases is increased. So what are the steps to calculate the chi-square? Now, the format conventions are that the independent variable is typically at the top, and the dependent variable is typically on the sides. So here you can see creating a contingency table. You can see the variables, the values or categories for those variables, the cells. The row marginals is the marginals that are in a column that measure values inside the total, rather, the values inside the rows. The column marginals are the marginals at the bottom of columns. You can see the total number of respondents is the intersection between the column marginals and the row marginals. So these are the steps to calculate the chi-square. Step 1, we total the column marginals by adding up all the column values. And you can see that's being done here. So we have low, medium, and high support as the dependent variable for a particular policy. And we've got female and male as the independent variables. Right? So we have two categories. So we've added 15 plus 15 plus 25 in the female column to equal 55, and 5 plus 15 plus 25 in the male column to equal 45. We totaled the column marginals. In step 2, we totaled the row marginals by adding up all the row values. So here we've added low support, female and male. 15 plus 5 is equal to 20, then 15 plus 15 is equal to 30, then 25 plus 25 is equal to 50, and then we total the values at the bottom of female and male column, and that equals 100. And you'll notice that the column marginals and the row marginals are equal to each other. Right? And we can we get the grand total marginal here. So in step 4, we're going to calculate the expected values for each cell. So for each cell, we're going to take the column marginal value. Let's take a look here at the value at the bottom of female. The value there is 55. We're going to multiply it by the row marginal, which for female and low support is going to be 20. You can see that as the extreme right in the total column. And then we're going to divide by the total marginal, which you can see as the total number of respondents, 100. It's the intersection of the column and the row marginals. So it's going to be 50 times 20 divided by 100, and this value is equal to 11. And we're going to make this calculation for each of the cells. Here you can see how we make those calculations. You can see the cell calcs section, which is 4 columns from the left. You can see the calculation for the first cell, a female and low, is going to be 55 times 20 divided by 100 equals 11. We've already calculated that. You can see the result is a red 11. We then calculate 55 times 30 divided by 100, where 55 again is the value at the bottom of the female column. 55, we multiply that against 30, which is the value at the end of the row, indicated by medium support, and that's 30. And we divide that again by 100, and that calculation will give us 16.5, and you can see the red 16.5. We then calculate again a female, marginal 55, multiply that against 50, which is the value in the total columns, and at the end of the high support. We divide that by 100, that equals 27.5, and you can see the red 27.5, which has been calculated. Now for the male values, we take the bottom value of 45 at the bottom of the male column, multiply that by 20, which is the value for the low support, divided by 100, that equals 9. You can see the red 9's been assigned. We have 45 times 30, which is the value at the bottom of the male column, times 30 end of the row for medium support, divided by 100 is 13.5. You can see the red 13.5. And we have the value at the bottom of the male column, 45 times 50, which is the value at the end of the high policy support row, divided by 100 is equal to 22.5, and you can see the red 22.5. So that takes us through step 4. And you can see here the results of those calculations. In step 5, for each cell, we square the difference between the observed, which is the actual value, and the expected frequencies, which we just calculated. Then we divide by the expected frequency. So example, for a female and low support, we take the value of 15 minus 11, we square it, and we divide it by 11, and that gives us a value of 1.45. So here we do the calculations more clearly. You can see in the cell calcs column on the right, we take 15, which is the intersection of low support and female. We subtract from it 11, which is the expected value. We square that difference, and that gives us 1.45. The next cell, we take the value of 5 for male and low support. We subtract from it the 9, which is the expected value. We square the difference, and we divide by 9, and that gives us a value of 1.78. In the third calculation, we take 15, which is the intersection of female and medium support. We subtract from it 16.5, which is the expected value. We square it. We divided it by 16.5 again, and that gives us a value of 0.14. In the fourth calculation, we take the 15, which is the intersection of male and medium, subtract from it a value of 13.5, which is the expected frequency. We square it, divide it by 13.5, and that gives us a value of 0.17. In our fifth calculation, the intersection of female and high support for a policy, we have 25 minus 27.5, which is the expected frequency, squared, divided by 27.5 is equal to 0.23. And our last calculation, we take 25, which is the intersection of male and high support, subtract from it 22.5, which is the expected frequency, divided squared, divided again by 22.5, and that gives us 0.28. And here you can see those calculations in steps. So in step 6, we total all of the cell values in the final calculation. 1.45 plus 0.14 plus 0.23 plus 1.78 plus 0.17 plus 0.28. That gives us a total of 4.05. Now we calculate a 5% as 2 degrees of freedom. And then we consult the chi-square table to see the value. Now in step 7, we calculate the degrees of freedom. And this is determined by the minimum number of cells filled, so we can deduce the missing values. And we calculate the degrees of freedom as the total rows minus 1 times the total columns minus 1. So this is a 3 by 2 table, so it's 3 minus 1 times 2 minus 1 is equal to 2 times 1 is equal to 2 degrees of freedom. Now the 8th step is to consult the chi-square table. And here you can see the chi-square table being represented. Let's point up a pointer option. So we can see here the 5% level of significance, which is pretty standard. This here is the degree of freedom that we calculated, and it gives us a critical value of 5.99. So we compare the value we calculated as 4.05 and the critical value, and what we want to do is have our calculated value exceed the critical value. In this particular case, it doesn't. We failed to reject the hypothesis that there is no association. So we see a false positive. We look at this relationship and we go, you know what, it looks like gender does explain something, but in fact it doesn't. Gender, in this particular contingency table, has no predictive or explanatory power and is not associated with the difference, the apparent difference between male and female. So what's the general interpretation? Well, the number must exceed the critical number for the null hypothesis to be rejected, which states that the sample relationship occurred by chance. In other words, didn't occur at all and was not observed in the population. Now, Kramer's V is a statistic applied to symmetrical contingency tables, one in which the rows and the columns are the same. It's based on the chi-square statistic. The formula is the square root of the calculated chi-square value divided by the total number of cases times k, which is the smaller of the rows or columns, minus 1. This is then going to give us the Kramer's V. So for example, we have in the previous case calculated a chi-square of 4.05. If we imagine a 3 by 3 table, that's got 2 rows or 2 columns. It's going to be 3 minus 1, which is a 2. And we multiply that by the total marginals, which is going to be 100 in the previous case, because that's the number of cases that we had. So it'd be 4.05 divided by 2 times 100, and we get the square root of that. And that's going to give us a value of 0.142, or 14%. So here we have the table that we used earlier. We can see that we've got a dependent variable, liberal, reform, NDP. And we've got in 3 categories. And we've got an independent variable with 3 categories, West, Central, and Atlantic. And so we have a 3 by 3 table here. So one of the calculations is going to be taking the 3 rows or the 3 columns, subtracting 1. That'll give us a k is equal to 2. And you can also see the total marginal here being 100. So it'll be 100 times that value of 2, which is going to give us a divisor of 200. So we calculate Kramer's V, where V is equal to the square root of the chi-square divided by the total marginals times k minus 1, where k is equal to the columns of the rows, whichever is smaller. So k is equal to 3 minus 1, which is the number of columns or rows minus 1, is equal to 2 times 100 is equal to 200. So we take the square root of that, 40.62 divided by 200, and that gives us a square root of 0.203, which gives us a total value of 0.45. So the interpretation is that there's a moderate relationship which exists between between the region of residence and party affiliation, and then including the independent variable of region provides a 45% improvement in the strength of making the prediction. Now, a difference of means test. This is for normally distributed data. So what's the purpose? The difference of mean test facilitates the determination of the significance of the difference between the means of 2 samples. So given the average support for Trudeau among women and nationally, and this is 51% with an N of 8,000 and a standard deviation of 5%, while the average support for Trudeau among men nationally is 46%, with an N of 9,500 and a standard deviation of 6%. So, in our example, does gender have a statistically significant effect on support for Justin Trudeau, i.e. are women more likely than men to prefer Trudeau as Prime Minister? Now, the procedures for difference of mean tests is as follows. The equation is the first mean minus the second mean divided by the square root of the standard deviation of the first sample squared divided by the number of cases plus the standard deviation of the second sample squared divided by the number of cases in the second sample. Now here the standard deviation is SD and the standard error is SE, and S means the mean and N is typically the cases. So if you see a formula, those are the what they mean. So here we have in our first sample females, the standard deviation squared divided by n is going to be 5 times 5 is going to be 25 divided by 8,000. And that's going to give us a value of 0.003125. The second sample are the males, and they have a standard deviation squared divided by n, which is 6 times 6. And that's going to equal 36 divided by 9,500, which is going to give us a value of 0.003789. We then add serial 1 and serial 2, or steps 1 and 2, and that's going to be totaling 0.006914. We then do the square root of serial 3, which is going to be the square root of 0.006914, which is going to equal 0.083153. We then determine in step 5 the difference of means. So it's going to be the first mean minus the second mean. So that's going to be 51% minus 46% equals 5%. In step 6, serial 5 is divided by serial 4. So that's going to be 5 divided by 0.083153, and that's going to equal 60. So in step 7, we're going to proceed to do the test. Now, normally we'd go to the t-test chart, or if we had more than 120 cases, we'd go to the z-test chart. Now, here in the t-test chart, we would use the 5% two-sided level of significance, and we would choose 120 cases because we don't have an infinite number of cases. We have less than an infinite number of cases, but we have more than 120 cases. So we conservatively choose 120, and that'll give us an intersection of 1.9. Because we have more than 120 cases, we are going to use the z-test chart, and we're going to typically settle on 1.096 because it gives us our 0.975%, which, if you recall, is the 95% plus half of 5%, which is 2.5%. So in step 8, we have the hypothesis test. Now, we are seeking to falsify or reject the null hypothesis that the means of these two samples are different. Since the calculated difference of means score of 60, which we calculated earlier, is greater than the z-test critical value of 1.96, so 60 is greater than 1.96, then the null hypothesis, which is that there's no relationship, is rejected. So in this particular case, gender does matter. Now, we can apply this equally to the t-test. Here we could notionally estimate 102 cases, subtract from it the two variables equals 100. And we would choose a 5% on the two-sided value, and that would give us a value of 2. And since 2 is greater than 60, then even with a t-test score, assuming that we have a very few number of cases, less than 120, because otherwise we're using the z-chart, then also with the t-test, we soundly reject the null hypothesis that there is no relationship. Now, in your notes, there is a Mann-Whitty U-test, difference of means, which is for non-normally distributed data. Because the hypothesis test that we did here assumes that the data is normally distributed.